So, good morning to everyone. Welcome back to the last of these, the fifth and last of these lectures. So, before starting this lecture, let me very briefly summarize what we did last time. What we did last time was a summary of some of the milestones in the theory, in the basic theory of ordinary differential equations on the complex domains with rational coefficients. What we did was to introduce a classification of singularities and to describe solutions, existence of formal and analytic solutions in the vicinity, in the neighborhood of these singularities. Okay, so what I want to do right now is to first of all to introduce a bunch of numbers which quantify how much multivalued solutions of our differential equations are. So, as last time, we consider this differential equation. This is the set of singularities of the coefficient, and we will have a bunch of singularities. These are points of sigma. And we divided singularities into two classes, regular and irregular. And we also introduced a second classification of singularity according to their Poincaré rank. And singularities with Poincaré rank 0, that is Fuchsian singularities, are regular. And I show you also two results on the existence of formal solutions. If we consider Fuchsian singularities, let's assume that this is a Fuchsian singularity, well, I show you that there is an existence theorem for formal solutions with a certain expansion in the vicinity of this singularity, and actually that formal solution is convergent. On the contrary, if we consider an irregular singularity, I show to you a theorem of existence and uniqueness for formal solutions. But in that case, formal solutions are typically divergent, and nevertheless, they still give us information about analytic solutions of a differential equation. Namely, they prescribe the asymptotic expansion in sectors with vertex the irregular singularity. In particular, let me summarize the following. Associated to a singularity Z nu in fracture S, we have the following monodromy data, local monodromy data. So, in this lecture, I will continue to use the same notations of the last lecture. So, if the singularity is Fuchsian, then we had the following, a solution of the following form. We have a matrix invertible times a series expansion, which is convergent, times a term of this form. Now I always put the labeling nu because I am considering the singularities in nu. And also, in case of resonances, we have a further term this appears only in case of resonances. And this is a matrix, I recall you, which put in Jordan form the coefficient A0, which is the leading term in the Laurent expansion of a coefficient around the singularity Z nu in Jordan form. Well, as from this formula, it is immediately clear that the responsible for the multivaluedness of solution of this form are these two exponents. This is just a matrix, a constant matrix with respect to z. This is a power series in integer powers of a local variable xi nu. So the only responsible for multivaluedness are these factors. And for this reason, we will call the pair lambda 0 nu and R nu, in case of resonances, will be called the local monodromy data at Z nu. In case of an irregular singularity of Poincaré rank R nu, well, we had a solution, we had a formal solution of this form, another times, well, actually we just an exponential of a sum of this kind, and well, the point was the following: that this formal solution is divergent, this series is divergent, and in the vicinity, I mean, if we consider the singularity, I told you that if we consider an arbitrary sector in the universal cover of a complement of fracture S, whose width is bigger than pi over R nu, then in such a sector there exists a unique, genuine analytic solution of a differential equation having this as a asymptotic expansion. Now the point is that I told you that if S is a Stokes sectors, then we can also rotate these Stokes sectors. So if this is the first Stokes sector, then I can rotate the Stokes sector, and the rotated sectors are always Stokes, and on each of them there exists, by the same theorem, a unique solution with this asymptotic expansion. Well, but all of these solutions are solutions of the same linear ordinary differential equation. So they can be related by multiplication by a constant matrix. So on each Stokes sector Sj, there exists a unique solution yj of z such that yj of z is asymptotic, as asymptotics the formal solution. And we can introduce the following matrices. We can consider the solution with prescribed asymptotics on the sector Sj plus 1. We can consider the solution on the sector Sj. The two solve the same linear equation, so they have to be related by some matrix independent of z, and this is called Stokes matrix. Or Stokes multipliers. So, in order to describe the monodromy, I mean, in the vicinity of an irregular singularity, what we have in our hand is something richer to be described. This is Stokes phenomenon. We have different solutions with the same asymptotic expansions in different sectors. And I will call at an irregular singularity local monodromy data a different bunch of numbers, namely the set of matrices lambda nu j, j from minus r nu 0, and the Stokes matrices from j equal to 1 to r nu. Let me recall you what these objects are. These objects are these diagonal matrices appearing in this sum plus this term. So these data will be called the local monodromy data at z nu. So what I did now was just to give a name to objects that we already introduced last time. And these matrices describe locally the multivaluedness and monodromy of solutions close to this singularity. But actually what we would like to have is a global picture. So what we need to do, what I want to do, is to introduce I want to glue all this data together. And in order to do that, what I will do is the following. I consider a point which is not a point in the complement of factor S. I also consider, I fix an invertible matrix Y0. I know that there exists a unique solution, say on a sufficiently small disk, which a solution of this differential equation whose value at z0 equals the fixed matrix Y0. And what I can do is the following. I just fix for each singularity, I fix the choice of a canonical solution. That is to say, at a Fuchsian singularity, I fix a solution of this form. At an irregular singularity, I fix once for all the choice of a Stokes sector. On this Stokes sector can be rotated, and the rotated sectors are Stokes sectors. We know that in irregular singularities we have a unique formal solution. Once we have fixed a Stokes sectors, on each Stokes sectors I have solution, and I can, okay, so by choosing a canonical solution at the singularity, I mean to fix a choice for a solution of this form at Fuchsian singularity, and a solution on the chosen Stokes sector at an irregular singularity. And what I can do now is to relate the solution I have at this regular point, so not a regular singularity, but just at a regular point, I can relate this unique solution with the chosen one at each singularity. That is to say, I am doing the following. So let Z0 in the complement of fracture S, Y0 in GLNC. We know that there exists a solution, a unique solution Y tilde of Z, solution of equation 1, such that Y tilde Z0 equal Y0. And now, if I consider a Fuchsian singularity, then I introduce the following matrix. I take this solution and I also consider this solution at this canonical solution at the Fuchsian singularity. I compare with this one, and the two must differ by a constant matrix, so I introduce this matrix. And this will be called a central connection matrix. At an irregular singularity, I do the same. But now I fix, as I said, a single Stokes sector, and by the way, this is, sorry, here you fix 1, 2, 3. If you check, the numbering of sectors should start with 1. If I didn't commit mistakes with my notations. And so I will have S1. I will have a solution Y1 on the sector calligraphic S1. And again, I can introduce another matrix, and so these matrices, which glue together canonical solution at singularities with a fixed arbitrary solution of equation 1, will be called central connection matrices. Of course, as you understand, these matrices are defined only up to choices of a regular point and of an invertible matrix. Actually, I can also do something else. I could, for example, not consider a regular point. I could consider, I choose one of an irregular singularity, one of a singularity in fracture S. I fix once for all a choice of a canonical solution at that singularity, and I use that fixed one solution in order to compare it with all other canonical solutions at other singularities. The important point is that we needed to introduce a bunch of matrices which glue together all the data we have. Okay. let me also introduce a different notation, a different name, terminology. So the set of all local monodromy data and central connection matrices deserve a name. So I will denote this by small m. So in this set I will have lambda 0 nu. The matrices are sigma. The Stokes matrices S, J, mu. And also the central connection matrices as C nu. Well, let me write all the indices, but so nu labels all the singularities from 1 to k. Sigma run only along the Fuchsian singularities. So assume that sigma, which is Z1, Zk, assume that the first P are Fuchsian and the last are irregular with Poincaré rank greater than 0. So sigma will be from 1 to P, and the mu goes from P plus 1 to K, and also J will go from 1 to 2R mu. So this is just a pedantic way to list all the data we introduce. And I will call this set of matrices the set of monodromy data. Is called set of monodromy data. Moreover, let me do an important remark. If you know this set, if we have a complete knowledge of this set, we are able to reconstruct the monodromy matrices along loops around the singularities. Indeed, assume, so this is an important remark, assume that gamma 1, gamma k are loops in the fundamental group of a complement of the singularities based at some regular point in one-to-one correspondence with, so gamma j is a loop around the singularity Zj, then we have the following two identities. The monodromy matrix gamma nu equals C nu inverse times the exponential of 2 pi I lambda 0 nu exponential of 2 pi I r nu times C nu. So in other words, the monodromy, in the case, Z nu is a Fuchsian. Z nu Fuchsian. So in other words, as you can see already from here, the local monodromy matrix around Z nu equals exponential of 2 pi I lambda 0 nu times exponential 2 pi I r nu, and this is this term in the middle. But in the monodromy matrix computed with respect to the loop gamma nu is in the same conjugacy class, and we need to multiply on the left and on the right by the inverse or the matrix C nu. In the case of an irregular singularity, we have something richer. We have something richer, and let me write it. Let me write it here. Yeah. Also, this can be deleted. In the case of an irregular singularity, we need to use Stokes matrices, and one can show that indeed the monodromy matrix around the loop gamma nu in this case equals the inverse of C nu times the exponential of 2 pi I lambda 0 nu times the product of the inverses of all the monodromy matrices attached to the nu times the connection matrix C nu. So this in case Z nu is irregular. In both cases, the message I want to send you is the following, that this set of monodromy data is a richer information than just the monodromy matrices. Because we have introduced a factorization of the monodromy matrices in terms of these central connection matrices, formal monodromy exponents. These matrices are called formal monodromy exponents because they are is the contribution to the monodromy coming directly from the formal solution. You see? Okay. Okay. This is just a lot of terminology. I have introduced the data that we want to introduce. Indeed, remember what I said last time is that we want to arrive we want to introduce at the end of the day some local invariant for Frobenius manifolds. Well, but right now, what the picture I described is just, so to say, a static picture. Because what we have here is just a single differential equation. And in the case of Frobenius manifolds, I show to you that there is a naturally attached joint system of differential equation, one equation of which can be interpreted as a family of differential equations whose coefficient depends on deformation parameters. These deformation parameters are the points. So what I would like to do now is actually to go from this static picture, a single differential equation, to the case of families of differential equations. So what I want to do now is I want to discuss, so to say, admissible deformations of a linear ordinary differential equation. So what I mean by that, I mean that now we have to handle with a family of differential equations where now we have deformation parameters which will be, say, variables in a, say, polydisk in CM. And now we will have T-dependent singularities. I will denote always by z nu, but now z nu will be functions from omega to p1. And nu, as before, I use the same notation, runs from 1 to k. So now the picture we have is the following. Here I put pi 1. And here I put the space of deformation parameters. And now I have singularities that vary with respect to the time. And the coefficient A, zt, the coefficient will be a function. So I will call by, let me call, maybe it's not a very good notation, let me call capital Z mu. Let me denote the graph of the function Z mu, seen as a function from omega to p1. So these strings are Z mu. And now our coefficient A is what? Is an holomorphic function on the complement of these strings. So is an holomorphic function in the complement of these strings. But it is a matrix valued function. So times M and C. Let me erase this. So we have these coefficients, which are holomorphic in the complement of these strings and with values matrices. Well, but of course I want to develop, so to say, a tame theory. And in order to do that, I will assume some genericity assumptions. So what are these genericity assumptions? Are the following. Well, first of all, I assume that these strings never intersect each other, for example. So I assume that there exists a family of disks delta nu from 1 to k, such that the closures of these disks never intersect, and such that the variable z nu of t, the singularity z nu depending on t belongs to this disk whenever t is, for any value of a parameter. Then I will also assume that the Poincaré rank of each singular point does not depend on t, is t independent. Third assumption is that the Jordan form of the leading terms A nu minus R nu, which now will be functions of t, in the Laurent expansion of the coefficients around z nu of t. So you take the coefficient, you consider the Laurent expansion at these singularities, it will have a leading term, and I assume that this Jordan form is t independent. And in particular, this leading term has a simple spectrum for all values of the deformation parameters in case z nu is irregular. Moreover, so this is an important assumption. This is just, you remember, when I developed the static theory, I required a main assumption that leading term, A minus R nu, is with simple spectrum. This is a dynamical extension of that main assumption, you see? For any value of the deformation parameter, we assume this. Then, last two requirements. The first requirement is that at each irregular singularity, we can choose a family of Stokes sectors such that if we translate them, if you fix a point and you translate all the chosen Stokes sectors, say corresponding to the first one, you fix S1, then they all coincide, these translations. That is to say, at each z nu t, a family of Stokes sectors as Sj nu j from 1 to 2 are nu can be chosen so that their images under the map, the maps z goes to z minus z nu of t is the same for all t in omega. And finally, I will also assume that all the solutions all the canonical solutions, which now depends on t in the case of Fuchsian singularities and the canonical solutions at an irregular singularity, so nu from p plus 1 k, are holomorphic with respect to t and their asymptotics hold uniformly with respect to t. So I wanted just to write down the formal definition of what an admissible deformation is. So the precise definition. So a deformation, a family of equation of this kind can be interpreted as a deformation of a fixed equation, and we will say that the deformation is admissible if it satisfies these 5 requirements. One can show that indeed all of these are not very strict requirements. I mean, are generic, so to say, are generic conditions. But this is important. 3. Independence of Jordan form. Okay, in this picture, we can find the picture we had, in which the parameters t are points of a Frobenius manifold. Well, but now, actually, I don't want just to develop a deformation theory, but I also want to introduce some invariants. And in that sense, I would be interested, for example, to understand under which conditions the monodromy, in a vague sense, of a family, of an admissible deformation, is constant with respect to t. Well, indeed, we can introduce 2 more precise notions. We will say that the admissible deformation 2 is weakly isomonodromic So a first notion is that of weakly isomonodromicity if a fundamental system of solutions can be y, z, t can be chosen so that the monodromy matrices M gamma nu t. So now we have movable singularities, and we will have movable loops around these singularities. Are t independent. So the first requirement is the following, that we will say that this deformation, this family of equation, is weakly isomonodromic if the monodromy matrices around all singularities are independent on T. But actually we introduced a stronger set of information, this monodromy set. And I show to you that the elements of this monodromy set are factors for the monodromy matrices. So I will call it strongly isomonodromic. The deformation if a fundamental system of solution can be chosen so that the whole set of monodromy data M, that is to say lambda 0 nu, R sigma, Stokes matrices, and central connection matrices, is T independent. Of course, the terminology is chosen so that strongly isomonodromicity implies weakly isomonodromicity. This is obvious from the remark I did here. Well, we have a following remarkable theorem, a first remarkable theorem. The admissible deformation is weakly isomonodromic if and only if there exist functions θ1, θm. I recall you that m is the number of deformation parameters, which are holomorphic on the complement of the strings such that we have the following system of equations. D over dtj y zt equals, or better to say, such that for any solution, y zt of 2, we have I write here the following set of equations. dy over dtj equals theta j times y, j from 1 to m. So, in other words, we have the following. A deformation is weakly isomonodromic if and only if there exist holomorphic functions on the complement of these strings in this cylinder, such that we have a joint compatible system of equations with the given one. How to see this? How to see this? Well, proof. So in one direction, just set the function theta j zt to be defined, transform this relation in a definition, and to be defined by this identity. And we have to show that these matrices theta j are holomorphic. That is, we don't have that these strings are not branch loci for these functions. But for that, notice the following. Delta j of, so I evaluate this function, so I need to prove that theta j, if we consider the analytic continuation along in Z along a loop, this equals by definition and this equals by definition of monodromy matrices, we have this equals y zt times the monodromy matrix gamma k times the same y zt times monodromy matrix gamma k. But if we assume that these are not dependent on the deformation parameters, we see that this object simplifies to dj y zt times y zt inverse, which is exactly theta j z of t. So in this direction, this proves that these strings in this cylinder are not branch loci for the functions theta j. The t's are well defined, these functions theta j are well defined and single valued in this. Sorry, yes, -1. Thank you very much. Thank you very much. In the other direction, assume that we are given the following joint system. So assume we have the zy equals azn of t times y, and the jy equals theta j times y. So we have this joint system. Then notice the following, that also the following identity holds true. I can just, if this identity holds true, I can analytically continue both sides in Z, and I obtain the following identity. Gamma nu zt equals theta j gamma nu zt times y gamma nu zt, and by assumption this equals theta j zt times y gamma nu zt. So here what I wrote is the following. I evaluate this I consider a loop in the z direction along gamma nu. I use this identity holds true identically in Z, so this must be equal to that, but by assumption this is holomorphic, so here I can delete this gamma nu. It is single valued. Okay, and it is single valued. But then we have the following. We have that the j of yzt times monodromy matrix m gam nu, which a priori depends on t, equals theta j zt times y zt times the same matrix m gamma nu, depending a priori on t. But if I expand this, I obtain delta j y times m gamma nu plus y dj m gamma nu, and this equals theta j times y times m gamma nu. But this cancels this, and y is a fundamental system of solutions, so it is invertible, and I obtain that the matrices are constant with respect to the deformation parameters. So this proves this remarkable characterization of weakly isomonodromic deformations. In the case of strongly isomonodromic deformations, we have a more deep result. We have a more deep result, which is the following. So for sure, since strongly implies weakly, we know that there exist these functions, holomorphic, in the complement of these strings. The point is that if we assume that the whole set of monodromy data is fixed, then the behavior of this function θ1, θm along these strings is under control, and in particular it is of polynomial growth. And indeed, we have the following remarkable theorem. If the admissible deformation is strongly isomonodromic, then the functions θj have polynomial growth along the divisors z mu, and in particular for any t in omega, the function θj at fixed t is a rational function. Is a rational function on P1. And for rational function on P1, we can consider the partial fraction decomposition. And let me just write the following let me write the following identity. What is the behavior of this function θj in the if we expand this identity in the vicinity around the singularity z nu? It is the following. So around z nu, we have the following expansion θj z of t. Since we have this identity, that is, we have this, and we know both at Fuchsian and irregular singularities what is the asymptotic expansion of solutions, we can replace such expansion in this identity, and we obtain that this has the following asymptotic expansion. It will be a matrix P nu that now depends on T. Then we also have a function, a series in which depends also on T, times the derivative of a function lambda, capital lambda of T, times the inverse of the same minus 1 plus order terms which are big O of 1, big O of 1 for, well, for xi nu going to 0 in the disk with punctures. And let me recall you who is lambda, capital lambda. Capital lambda So capital lambda is capital lambda xi nu t equals the sum r nu minus 1 lambda nu j t over j xi nu j plus the matrix lambda 0 nu. So this formal monodromy exponent log of xi nu. Log of xi nu. And I color this because by assumption this is independent of t. You see, if it is strongly isomonodromic, this is independent of t. And let me also do another remark. When I proved the existence, I didn't prove how to compute these matrices in the formal solutions, but because I didn't prove the theorems. But I told you, just take this as an ansatz, put in your equation and try to solve the equation. Well, if you do that, you realize that indeed these coefficients in these expansions f, these series f, can be computed in terms of the coefficients of the equation, the coefficients A of the equations. So what does it mean that? It means the following, that this theta j can be computed in terms of the coefficients of the equation themselves. You see? Okay, I think it probably is better to do a pause. so let's summarize what we have understood. We have understood that in order to have a weakly isomonodromic system, we need necessarily to have a joint system of equations, as many equations as deformation parameters. This joint system must be integrable, and the integrability relations are, as usual, the following equations. A nonlinear system of differential equations in the coefficients. You see, as I said, here is J. As I said, the coefficients, the functions theta j can be computed in terms of the coefficients A. So we can interpret this nonlinear system of equations as a nonlinear system of equations for the coefficients of A itself with respect to their dependence on the deformation parameters T. Well, a priori, this is a necessary condition in order to have strongly isomonodromicity. A very deep theorem by Jimbo, Miwa, and Ueno tell us that actually this is also a sufficient condition in order to have strongly isomonodromicity. Jimbo, Miwa, Ueno, 1982. The admissible deformation 2 is strongly isomonodromic if and only if these equations holds. Hold identically in Z, and where the coefficients theta j are computed via the asymptotic expansion I wrote before. So I repeat, this asymptotic expansion allows us to compute theta j as in terms of the coefficients A, where theta j are expressed in terms of the coefficients A. Now, this system of nonlinear equation is an overdetermined system of nonlinear equation, and a priori there is no reason for which it should be integrable itself, this system. Well, it is also a result of Jimbo, Miwa, and Ueno that the system free is integrable in the sense of Frobenius and moreover, so what they did was the following. They consider this big joint system of nonlinear equation. They found a minimal set of independent equations. They proved that this is integrable in the sense of Frobenius, and they also proved that the remaining equations of these systems are algebraically dependent on the minimal one. And in particular, they proved that, moreover, the largest set of deformations deformation parameters independent, I mean the largest set of independent deformation parameters can be chosen as the singular points z nu and the diagonal matrices lambda minus h nu. So these matrices, these diagonal matrices which appear in the exponential term of formal solutions at irregular singularities. So mu runs from 1 to k. Okay, let's. I mean, we also include singularities, and h equals 1 to r nu. So one can always assume. So in other words, one can always assume that the number m of deformation parameters equals k, the number of singularities, plus n, the size of the matrices, times the sum of the Poincaré ranks from 1 to k. And t, the parameters of deformation t, coincide with the singularities z nu and lambda minus h nu, where nu again from 1 to k and h from 1 to r nu. Okay, this is the general theory, but let's see in a concrete example how all this machinery works. For example, which is the main example on which we should focus on. So consider a system with two singularities only. So this is a diagonal matrix U1, Um. And this, for the moment, is an arbitrary matrix. It's an arbitrary matrix with Jordan form, with diagonal Jordan form. With diagonal Jordan form, and I will denote this diagonal Jordan form mu. So I am starting to use the notation in such a way that in your mind you should start to identify who is who. So right now it's not clear, but you will see that in a minute you will recognize many things. So we want to study isomonodromic deformation of equation of this kind. We have only two singularities, one at 0 and another one at infinity. At infinity. at 0 we have a Fuchsian singularity, at infinity an irregular one. And we want to study the Iso Monotromicity deformations of this. I just said that we can assume that the deformation parameters are what? Are the eigenvalues of U and these diagonal matrices appearing in the formal solution expansion, in the expansion of formal solutions. So let's write down what we have. So we have the following. The eigenvalues U1, Un can be chosen as deformation parameters by this theorem of Jimbo, Miwa, and Ueno. So that if we are interested in describing isomonodromic deformation of this equation, now the coefficient V will be a function of the deformation parameters, that is of U. So that V is assumed to be of a form V depending on U. Moreover, at z equal to 0, we have fundamental systems of solutions of the following form: y at 0 depending on z and u to be equal p matrix P depending on the point times identity plus a power series depending on u, the power j from 1 to infinity, times z mu times z r, where r is here only in case of resonances of eigenvalues of mu. Resonances of eigenvalues of mu. So here mu is this Jordan diagonal form. And okay, we want to study strongly isomonodromic deformations of this equation. Then necessarily we have to impose that mu and r are independent on u. So in particular, mu and r are independent on u. I am just describing what are the possible, what is the form of isomonodromic deformation for a system of this type. At infinity, we have the following formal solution. We will have 1 plus a matrix over Z plus higher terms in 1 over Z times a polynomial term in a certain diagonal matrix lambda 0. For the moment is not clear who is it, and then an exponential term. And in this exponential term, we have exactly this matrix U. I leave to you as an exercise to convince yourself that this is the form that the formal solution must have. And we know also that this, by the theorem of last time, this must be diagonal. Diagonal and independent on U, because we want to study isomonodromic deformation. So diagonal and U independent. But let's do the following. Let's try to compute these objects. So what I do, I take these ansatz I put in this equation and I start to compute all these objects. And I find, so impose, this is a solution of equation 4 of 4. And we find the following. We have a term of this kind, time plus identity plus f1 over z plus f2 over z square plus higher order terms times u plus lambda 0 over z. So these terms comes from the derivative of this guy. And this must equal u plus v over z 1 plus f1 over z plus f2 over z square plus ta ta ta. So this equation can be obtained by taking this, you put here, and you also delete this. I mean, you compute the derivative, and then you can cancel out this term, and you obtain this equation. And this must also identically in z. So let's start to compare powers of z. What we have. So for z to the power 0, we have an identity. U equal u. Okay, nothing particularly deep. For z to the power minus 1, we start to find some strong constraint. The commutator of f1 and u must equal the difference of v and lambda 0. But here we have a commutator of a matrix with a diagonal matrix, and in particular it is off diagonal. But then necessarily lambda 0 must equal the diagonal part of v. So from this is off diagonal. And consequently, lambda 0 coincides with the diagonal of the matrix V. So you see, we start to find something interesting. And moreover, if I write down these in components and I look for the components ij, for the entry ij, for ij entry, you find the following. If you do the computation, you find the following equations, that f1 ij equals vij over ui minus uj. So when I and j are different, remember that by assumption, ui and uj are different whenever I is different from j. So here you are. We are able to express f1, the entries of f1, in terms of the u's and also v. But remember that v also is a function of u. So everything here is a function of u. And I leave to you as an exercise, try to compute the diagonal entries of f1. I give you an hint. Go further to higher order terms in Z. But for what I need now, I stop here. I mean, I stop with a computation of diagonal entries of f1. Okay, I claim that this is sufficient to compute the functions theta j. So how many functions theta j we have? Well, we have exactly, well, we can reduce this to be n to be just n, as many as the function, as the parameters u. So we can compute the coefficients theta j for j from 1 to n. And as I said, theta j are functions, are rational functions, and we have the polar fractional decompositions, and so we will have contribution coming from expansions around 0 and contributions from expansions around infinity. And how to compute these contributions? As I said, by doing the computation of you just take the exponential, the asymptotic expansions, and you take the singular part. So, that is to say, for example, theta j, the contribution coming from infinity, must so recall. So we have the following. Recall. Theta j must equals the y times y inverse. So what I do now, I take this equation, I replace y with its asymptotic expansion at infinity, and I cancel everything, I simplify as much as possible this computation, and at the end of the day, this function theta j must equal the singular part of this expression, singular at infinity. So and here I have just the inverse of this expression, but this is just 1 minus plus higher order terms, and I need to take the singular part at infinity, that is to say, powers of z with non-negative powers of z, yeah. And wait, but here, what is that? I have a diagonal matrix with ZU1, ZUN, and I am taking the derivative with respect to uj. So this becomes identity plus f1 over z plus z times ej, where ej is the diagonal matrix with all entries here except a single one at the position j, so I will write this later, times identity minus f1 over z plus and of this I need to take the singular part. But the singular part, so we have powers of z, so ej ik equals delta ji delta jk. So powers of z positive, we have z ej, and this is the only positive power of z. Then we have f1 times ej minus ej times f1, that is to say the commutator of f1 and ej, and all the remaining terms are big O of 1 over z. So I need to take the singular part at infinity of this, and this equals exactly these two terms. So z ej plus f1 ej. And in a similar way, using this expansion, you can compute also the contribution coming from 0. And then, so for doing this, you do exactly the same computation with this, and then you need to take the singular part at 0. And I leave to you as an exercise to prove that, indeed, this is identically 0, exercise. But then we have the following result, that the functions theta j, functions of z and u, are given by z ej plus f1 times ej. I recall you that f1 is a function of u because of this. And then let's write down the system, the following system of equations. We have the equation with which we started, that is and also z ej plus f1 ej y. And so we have this joint system of equations. And another exercise, check that the only non-trivial integrability conditions are equations in the functions v is a function of u. So the derivative of v with respect to uj must equal the commutator of f1 with ej and v itself. So these are the only non-trivial integrability conditions for this joint system. So these are nonlinear equations in V, and if V satisfies these nonlinear equations in V, with respect to U's, then this equation is strongly isomonodromic according to the theorems I presented before. Okay, we are going towards the end of this course, and now what is my aim is to glue all the things I told you, to glue together all the things I told you. So we started with a Frobenius manifold, and we arrived to attach to this Frobenius manifold a joint system of equations. By using the extended deformed connection. So, for Frobenius manifold, using the extended deformed connection, which is flat, we obtain a joint systems of equation. These are derivatives with respect to the flat coordinates. Because, recall, Greek indices are with respect flat coordinates, with respect to the Levi-Civita connection. But, yeah. So how to glue together everything? Well, I claim the following. Claim this system 5 probably it's better to call this 5 and this 6. So system 6 is gauge equivalent to a system of a form 5. And what is this gauge equivalence? It's the following. Define, so start, take the idempotent vectors of the Frobenius manifolds, the idempotent vector fields, and normalize these vector fields by using the metric eta, and here we have a choice of signs in square roots. So what we are actually defining here is not a, I mean, is a section of some torsor over the Frobenius manifold, and because we have freedom in the choice, so what is the picture? The picture is this. We have the Frobenius manifolds, and we have idempotent vectors, pi I. I normalize these vectors, and these are Fi. But then we also have flat coordinated vector fields. This is d alpha. And so what I introduce now, I introduce a matrix of change of basis defined as follows. It is the matrix which expresses the change of basis from the flat coordinated vector fields and this orthonormalized idempotent frame. So this is how this matrix psi is defined. And we have, by the way, I leave to you as an exercise, the following identities. Very easy to prove. Psi transpose times psi equals eta. Psi, all the equality I am writing down are equality of matrices. Psi entries I1 equals the square root of the norm of pi I. We can reconstruct the normalized idempotent vector Fi by taking this sum, psi I1, psi I beta, eta alpha beta in d alpha. And last, C alpha beta gamma equals psi I alpha, psi I beta, psi I gamma over psi I1 from 1 to m. Now, if you set Roman y to be equal curly y, this curly y, times pardon. So it's a gauge equivalence. So now multiplication is on the left. Psi times y then I leave as an exercise to show that this system is equivalent, using this gauge equivalence, to the following one. So this was a system for curly y. I use this, and I obtain a system for Roman I. The derivative now, here I am considering derivatives with respect to canonical coordinates, equal z ei plus it's a gauge equivalence, so this times y, and here we have z y equals u plus 1 over z v times y, where u is the diagonal form of the operator of multiplication by the Euler vector field, and v is the grading operator in this idempotent frame, and by recalling that mu is eta skew-symmetric, you can prove, and this together with this identity, you have that V transpose plus V is 0. That is, V is an antisymmetric matrix, and moreover, from this same equation, if you take the derivative with respect to I, you discover that these matrices Vi, let me call these Vi, are antisymmetric. But then you recognize immediately that this system, which is just this written in a different frame, tangent frame, is exactly of this form. And that means, if we have, from this general theory, we know that if we compute the monodromy, the set of monodromy data for this equation, which is an equation whose coefficient depends on u, the canonical coordinates u, so on the points of the Frobenius manifold, you realize that because of the existence of this further term, of existence of this compatible joint system of equation, you deduce that the set of monodromy data is independent of the deformation parameters. But then, what is the picture? How much time? What is the picture we have? We have the following picture. This is our Dubrovin Frobenius manifold, and I can fix an oriented ray an oriented line L in the complex plane L. And attached to each point of the Frobenius manifold, I have the eigenvalues of the operator U. So here we have a bunch of points Ui, eigenvalues of U. And I can introduce these Stokes rays. I can introduce the Stokes rays by these equations. Rij equals minus rho times imaginary unit, Ui complex conjugate minus Uj complex conjugate where rho is a real positive number. So to each point, I have a configuration of canonical coordinates. To this configuration of canonical coordinates, I can attach a configuration of Stokes rays. And these Stokes rays, so Rij, Rji, are such that, and we may also have other. And we can consider the open set of points of the Frobenius manifolds at which the fixed oriented line does not coincide with one of the Stokes rays. And well, there will be points at which some Stokes rays coincide with oriented line. So I will discard these points. And this will define a decomposition of the Frobenius manifolds into pieces. Each piece will be called an L chamber of the Frobenius manifold. And moreover, we can also use this line, this oriented line L, to define two Stokes sectors. One Stokes sectors, so one Stokes sector, we have a line, one Stokes sector will be defined by a slightly bigger half plane on the right of the line, and the other one will be on the left. Of course, this sector should be interpreted in the universal cover of C star. And according to the general theory we discussed in the last lecture, we will have a solution at 0 which will be of this form. Now the gauge, previously I denoted by P nu the matrix, now it is exactly this gauge. And this is convergent. And we will also have a formal solution of a form, we have a power series times an exponential term only. And notice that by this relation, the matrix V is antisymmetric. Consequently, its diagonal terms are 0. And I proved in the computation of the previous blackboards, that the exponent lambda 0 must equal the diagonal part of V. In other words, I am saying that for Frobenius manifolds, the formal monodromy is vanishing. Okay? So we don't have a further polynomial term in Z. And this is a formal solution, but this gives me the asymptotic expansions for two solutions in Stokes sectors on the right and Stokes sectors on the left of the line L. And I can introduce exactly as I did in the general picture before, a connection matrix which relate the solution at 0 and the solution on the right, and a Stokes matrix which relates solution on the right with solution on the left. Well, according to the general theory we developed before, we have the following remarkable property. Inside each L chamber, the monodromy data mu and r, which comes from the solution at 0, and Stokes matrix and central connection matrix, so the set of monodromy data is constant. So by using the flatness of a nabla flat connection, we were able at the end of the day to attach to each piece of a Frobenius manifold a bunch of numbers, mu, r, s, and c. And many things could be said. Let me choose some important comments to do. First important comment. Imagine you know the value of the monodromy data in one chamber. Are we able to predict the value in other chamber? Well, yes, we are. This was discovered by Dubrovin, of course. And we have the following. We have an action of the braid group on the set of the monodromy data. And why the braid group? Well, it is not so surprising. Indeed, let me consider a path. Imagine you know the data in point of a chamber, and you want to reconstruct the monodromy data in another point, say here. So you may choose a path which connects the 2 points, and if you follow this path, you will have a configuration of canonical coordinates, which are just points in the plane, which starts to dance. And if you recall the definition of braid group as mapping class group of a punctured disk, well, here you are why it appears, and we have a following action on the set of monodromy data. If we consider an elementary transformation which let rotate the value ui with respect to ui plus 1 in a counterclockwise ways, and if we identify this with one of a generator of a braid group, Bn, then we can, given S and C, a pair of Stokes and central connection matrix, we can introduce a matrix A beta I defined only in terms of S, which is a matrix with a single non-trivial 2 times 2 block along the diagonal given by 0, 1, 1, minus S I plus 1. That is, you take minus one of the entries of a matrix S itself, and then you have again, so you have a 2 times 2 block and then 1. And okay, so given S and C, you can introduce this matrix, and the Stokes matrix after this transformation, that is along a path here, which let's rotate these 2 points in this way, will change as follows. Multiplication on both left and right by the same matrix. The central connection matrix will change in this way. You multiply on the right by the inverse of this matrix A beta I, which is a function of S. So that is to say that we have a complete picture. We can, if we know the value here, we can reconstruct the values of the monodromy data in any chamber of a Frobenius manifold. 2 other important comments. First important comment is that clearly the numerical value of this data depends on the choice of many normalization, as you understand. Well, it depends. Let me summarize. It depends on the choice of the oriented line L. It depends on the ordering of of the labelings of canonical coordinates. It depends on the choice of the square signs in the square root, defining the idempotent frame that is in this gauge equivalence. And last but not least, it depends on the choice of a form of a solution at the origin. You remember last time I told you I never claim the uniqueness of solutions of, in leveled form at Fuchsian singularity. And indeed, all these ambiguities must be properly quantified, and this can be done. Let me finish with some very last comment. I also said that what we want to develop was a theory of, in order to find complete invariants, that is, invariants which allow us to classify these Frobenius structures. Up to now, I told you that these numbers are defined local invariants, but I didn't claim that they identify uniquely the Frobenius structures. Well, this is another important property that, imagine you know the value, the numerical value of the data in one point for one configuration, a single one configuration of canonical coordinates. Well, it is possible to reconstruct the whole Frobenius structure by setting a Riemann-Hilbert-Birkhoff boundary value problem. So you use as input the numerical value of this data, and you set down a Riemann-Hilbert-Birkhoff problem. If you are able to solve this problem, it is difficult. I'm not saying that it is easy to do, but still it is there. And if you are able to solve this, then through very explicit formula in literature, for example, you can find this formula in my last preprint, you are able to reconstruct explicitly all the tensors defining the Frobenius manifold. For example, this WDVV potential, which is at the core of the Frobenius manifolds theory. So many other things could be said, I hope. So when I was asked to give this course, I was asked to explain how isomonodromic deformations arise, for example, in algebraic geometry, singularity theory, and I hope to have given you a gentle introduction, as gentle as possible, to this research domain. And of course, I could continue for many hours, but it's better to stop. So I thank you very much, and